Fine. Let's start. Here's something that should bother you more than it probably does. Every rule we have for how planets work, how they form, where they're allowed to orbit, what they can be made of, we built those rules by studying 8 planets. 8 in one solar system, around one star, out of somewhere between 200 and 400 billion stars in this galaxy alone. For a long time, that was all we had. And honestly, the rules we built weren't bad. They held up pretty well. Until we started finding planets around other stars. And then the rules started bending. And then they started breaking. And then some of these planets showed up. And the rules just stopped applying entirely. These aren't weird edge cases that scientists quietly filed away. These are planets that forced papers to be retracted, models to be rebuilt from scratch, and actual astronomers, people who have spent their careers studying this stuff, to sit back and say out loud in print that they have no idea what they're looking at. 10 of them. Let's go. Number 10. The graveyard clue. There's a question that bugged astronomers for years, and it hides inside what looks like a pretty boring graph. If you plot all the exoplanets we've found by size and distance from their star, something strange shows up. You get tons of hot Jupiters, giant gas planets orbiting close in. You get tons of small super-Earths doing the same thing, but right in the middle, where you'd expect to find hot Neptunes, planets about the size of Neptune, orbiting close to their stars. There's almost nothing. A gap. A desert. For a while, the working theory was that Neptune-sized planets just don't end up in tight orbits very often. Formation quirk, statistical fluke, nothing to worry about. Then we found GJ 3470b, and the desert started to make a different kind of sense. GJ 3470b is a warm Neptune. It orbits a red-dwarf star about 96 light-years away, completing one loop every 3.3 days. And Hubble caught it doing something that no planet had ever been caught doing at quite this scale. It's losing its atmosphere. Fast. 100 times faster than the previous record holder. To put that in terms that feel real, the planet has probably already lost somewhere between 4 and 35% of its total mass just from stellar radiation stripping its hydrogen away. It orbits a young, active star, only about 2 billion years old, and that star is basically pressure washing its atmosphere into space. Lead researcher Vincent Bourrier at the University of Geneva called it one of the most extreme examples of a planet undergoing major mass loss over its lifetime. And David Singh from Johns Hopkins, who worked on the same study, put it plainly, in only a few billion years, half the planet may be gone. But here's the thing. If you do the math on what happens to a Neptune-sized planet when you strip away enough atmosphere, you don't get nothing. You get a rocky super-Earth, a small, dense, airless rock. Exactly the kind of thing we find everywhere in tight orbits. The hot Neptune desert isn't empty because those planets never formed there. It's empty because they evaporated. The catalog isn't a portrait of what exists. It's an archaeological record of what used to exist. Every super-Earth we've found hugging its star might be the skeleton of a Neptune that ran out of time. GJ 3470b is one of the last ones we caught still on its feet. Number 9. The rebel in the choir. Most planetary systems, when you look at them from a distance, make a kind of intuitive sense. Planets closer to the star tend to be smaller and denser. Planets further out tend to be larger and gassier. Think of our own solar system. Rocky inner planets, gas giants on the outside. It's not a law exactly, but it's a pattern, a tendency that falls out naturally from how planets form. TOI 178 has 6 planets. And it breaks this pattern in a way that genuinely has no explanation. 5 of those 6 planets, all the outer ones, orbit in something called a Laplace resonance chain. This is when planets' orbital periods lock into perfect mathematical ratios with each other. In this case, 2 to 4 to 6 to 9 to 12. Every time the innermost planet completes 2 laps, the next one completes exactly 1. Every time that second planet does 4 laps, the third does 2. And so on. It's a gravitational symphony. It means these planets have been nudging each other into perfect synchrony for millions of years without any of them getting flung out. That's remarkable on its own. Resonance chains are rare, and this one is one of the longest ever found. But then you look at what those planets are actually made of, and something breaks. Planet C is dense, rocky, Earth-like in its bulk. Planet D, right next to it, is roughly 17% as dense as Earth, less dense than water. In the next orbit out, density goes back up, then back down. There's no gradient, no logic. The compositions of these worlds are scrambled in a way that standard formation models simply cannot explain. Here's what's even stranger. In every other resonance chain we know of, TRAPPIST-1, Kepler 6003, the planet compositions tend to vary smoothly. The resonance and the structure go together. TOI 178 has a system that looks, from its orbital timing, like it formed with exceptional care and precision. And then, from its compositions, like something went very wrong somewhere in the middle. And one of the 6 planets broke free from the chain entirely. The innermost one sits just outside the resonance, nudged loose, probably by tidal forces from the star dragging it gradually out of sync over millions of years. It orbits a little too fast now, slightly out of step with the others. The lone rebel in an otherwise perfectly choreographed system. We have no unified explanation for why the orbits are so ordered and the compositions are so chaotic. No model accounts for both. The universe is following rules. We just haven't figured out what they are yet. Number 8. The football made of metal and fire. 900 light years away, there's a planet shaped like an American football. This is not metaphor. The star it orbits is so massive, and the orbit is so tight, that the gravitational tidal forces have physically deformed the planet, stretching it along one axis, squashing it along the other. WASP. 121b is a lump of gas with the rough proportions of a rugby ball, orbiting its star about 15 times closer than Mercury orbits the Sun. It completes one full orbit every 1.27 days. Its upper atmosphere reaches roughly 4,600 degrees Fahrenheit. And that heat is doing something that has no precedent in our solar system. In 2019, the Hubble Space Telescope detected magnesium and iron in WASP 121b's atmosphere, not in the lower layers where you might expect them, but high up. Startlingly high up. So high that they were no longer gravitationally bound to the planet. They were escaping. Iron and magnesium leaving the planet permanently, streaming away into space, not cycling back down as clouds, not condensing at altitude. Gone. Lead researcher David Singh described it directly. The heavy metals are escaping, partly because the planet is so big and puffy that its gravity is relatively weak. This, he said, is a planet being actively stripped of its atmosphere. That was the first time heavy metals had ever been detected escaping from any hot Jupiter. Not just unusual, first of its kind. But here's the thing. It gets stranger when you look at the atmosphere layer by layer. On Earth, temperature in the atmosphere decreases as you go up. That's just how it works. You move away from the warm surface. Things get cold. WASP 121b has a stratosphere where temperature increases with altitude. It runs backwards. And inside that inverted stratosphere, astronomers detected water vapor. Water, at these temperatures, in these conditions. Existing in a layer of atmosphere that shouldn't, by standard atmospheric chemistry, allow water vapor to exist. There's a version of this planet where it keeps losing material until it's stripped down to a dense, airless core. There's another version where it spirals close enough to its star that it gets torn apart entirely. Either way, the clock is running. A planet being dismantled piece by piece, molecule by molecule, in conditions we've never seen before. Atom by atom, it's becoming part of its star. Number 7. The cotton candy world. Imagine you could scoop up a chunk of WASP 193b. Just grab a piece of it, hold it in your hands. What you'd be holding would be lighter than the air in the room with you. Not lighter than styrofoam, lighter than air. This planet is so diffuse, so outrageously puffed up, that its density comes in at 0.059 grams per cubic centimeter. For reference, cotton candy, the sponge sugar you get at a fairground, has a density of roughly 0.05 grams per cubic centimeter. WASP 193b is, by any reasonable physical measure, cotton candy. Just a lot of it. Specifically, it's about 50% larger than Jupiter, and it has roughly 14% of Jupiter's mass. Jupiter is already enormous. WASP 193b is bigger than that, and somehow manages to have almost none of the mass you'd expect from something that large. For further comparison, if you dropped Saturn into a large enough body of water, it would float. Saturn is the least dense planet in our solar system. WASP 193b is less than a tenth as dense as Saturn, less dense than liquid water by a significant margin. Khalid Barkawi at MIT, who led the team that confirmed its existence and published the findings in March of 2024 in Nature Astronomy, described it plainly. Its extremely low density makes it a real anomaly among the more than 5,000 exoplanets discovered to date. Hot Jupiters can be inflated. We know this. Stellar radiation heats the atmosphere. Various mechanisms puff the planet up beyond what you'd expect. There's a whole class of planets called puffy Jupiters, and they're reasonably well understood. But even the most extreme versions of our inflation models run under the most generous theoretical assumptions, stripping away the core, cranking every dial to maximum, can't get you to WASP 193b. But here's the thing. The planet is roughly 6 billion years old. That's older than Earth. Inflated planets are supposed to contract over time. They're supposed to gradually settle, cool, condense. 6 billion years of cooling, and WASP 193b is still floating. Still as light as cotton candy. Still completely inexplicable. Barkawi called it, directly, a cosmic mystery. Not a puzzle with a solution pending. A mystery. Something that should not have lasted this long, that has lasted longer than we can explain, drifting around its star in quiet defiance of everything we think we know about how gas giants age. Number 6. The planet hidden in plain sight. In the year 2000, astronomers were conducting a survey. They were scanning the skies around various stars, looking for planets by direct imaging, actually photographing them rather than detecting them through stellar wobble or transit dimming. They pointed their instruments at B Centauri, a binary star system about 325 light-years away in the constellation Centaurus. They took images. They analyzed them. They found a faint object near the star, and they marked it as a background star and moved on. The image sat in an archive for 21 years. In 2021, a team led by Marcus Janssen at Stockholm University went back to B Centauri with the Very Large Telescope in Chile, using the SPHERE instrument, one of the most powerful planet imaging systems ever built. They imaged the system. They found something. And then they did what the 2000 team hadn't. They checked if it moved with the star over time. It did. It had been moving with the star the whole time. That faint object in the archive wasn't a background star. It had never been a background star. It was a planet, not a small one. B Centauri b is roughly 10 times the mass of Jupiter, making it one of the most massive planets ever directly confirmed. and the star system it orbits, a binary pair with a combined mass of at least 6 times the Sun, is the hottest, most massive planet-hosting system ever found. The primary star has a surface temperature of around 18,000 Kelvin. Our Sun, for comparison, is about 5,800 Kelvin. Here's why that matters. Stars this massive and this hot were considered off-limits for planet formation. They live fast and die young, fusing through their fuel in a fraction of the time a Sun-like star takes. Their intense ultraviolet radiation was thought to destroy protoplanetary disks, the clouds of gas and dust that planets are born from, before anything could accumulate into a world. No disk, no planet. That was the understanding. Janssen said it directly. Finding a planet around B Centauri completely changes the picture about massive stars as planet hosts. There's an argument that the planet survived because of its orbital distance. It sits roughly 100 times further from its stars than Jupiter sits from our Sun. Maybe at that distance, shielded by the sheer scale of space, it avoided being fried before it could form. But the image from 2000 was just sitting there. A planet, 10 times the mass of Jupiter, orbiting a system visible to the naked eye, hiding in an archive, waiting. 21 years is a long time to be a discovery that nobody noticed. Number 5. The planet on its last breath. There are 4 known disintegrating planets. Just 4 out of nearly 6,000 confirmed exoplanets. 3 of them were found over a decade ago by the Kepler Space Telescope. They've been studied, cataloged, and more or less filed away, known phenomena, no longer surprising. Then, in April of 2025, a team at MIT found a 4th one, and it's different from the others in a way that makes even the comparison unsettling. BD plus 054868 AB is a rocky planet roughly the mass of Mercury, orbiting a K-type star about 140 light-years away. Its orbital period is 30.5 hours. Not days, hours. It completes a full year in just over a day, screaming around its star at a distance about 20 times closer than Mercury orbits the Sun. At that proximity, the surface temperature is around 1,600 degrees Celsius. The rock isn't just hot, it's boiling. Minerals are vaporizing off the surface, and because the planet's gravity is so weak, Mercury mass objects don't hold on tight. Those vaporized minerals aren't falling back down. They're escaping, cooling as they drift, condensing into dust grains, forming a tail. Mark Hahn from MIT's Kavli Institute described the tail as gargantuan, stretching up to 9 million kilometers long, or roughly half the planet's entire orbital path. Both a leading tail and a trailing tail, which is unusual even among disintegrating planets. The other 3 only have trailing tails. This one sprays material in both directions. But here's the thing, it's worse than just evaporation. Because as the planet loses mass, its gravitational grip weakens. A weaker grip means more material escapes per orbit. More material escaping per orbit means less mass, means weaker gravity, means more escape. It's a feedback loop. The planet is accelerating its own destruction. Not metaphorically, the disintegration is literally getting faster over time. Avi Sporer, a collaborator on the discovery at the TESS Science Office, put it in terms worth sitting with. We got lucky with catching it exactly when it's really going away. It's like on its last breath. The team estimates the planet will be completely gone within 1 to 2 million years. In geological terms, that's the day after tomorrow. By the time multicellular life might be evolving somewhere nearby, if there were a somewhere nearby, the planet would already be dust, spread thin across the orbit of a star that used to have something to show for itself. There is no saving it. There is no intervention. The only thing we can do is watch and take notes while there's still something there to take notes about. Number 4. The backwards comet planet. Picture a planet's orbit. Most planetary orbits are nearly circular. Some are slightly elliptical. Earth's orbit has an eccentricity of 0.02, barely a squashed circle. Even Pluto, with its famously weird orbit, only hits 0.25. An eccentricity of 0 represents a perfect circle. An eccentricity of 1 represents a parabola, an object that isn't orbiting at all, just falling through the system once and leaving forever. TIC 241249530b has an orbital eccentricity of 0.94. That's not an orbit. That's a comet trajectory, and it belongs to a planet. This gas giant, 5 times the mass of Jupiter, was first spotted by the TSES satellite in January of 2020 and confirmed in a paper published in Nature in July of 2024 by a team led by Arvind Gupta at Penn State. Its orbit is so elongated that at its closest point, it passes within 6 stellar radii of its star, skimming extraordinarily close, flash heating to temperatures that could melt titanium. Then, it swings back out to distances comparable to Earth's orbit from the Sun. The temperature difference between its closest approach and its farthest point is staggering, mild to catastrophic in the span of a single year. A year that lasts about 167 days. All of that is strange enough, but it doesn't stop there. The planet orbits backwards. Almost every planet in every known solar system orbits in the same direction its star rotates. This isn't a coincidence. It's a direct consequence of formation. Stars and planets are born from the same rotating disk of gas and dust. The disk spins one way. The star spins that way. The planets orbit that way. It's angular momentum preservation, a fundamental expectation of the entire formation process. TIC 241249530b orbits in the opposite direction to its star's rotation. Retrograde. Against everything formation theory predicts. The Discovery team used an instrument called the NID spectrograph at Kitt Peak National Observatory to measure something called the Rossiter-McLaughlin effect, a way of detecting whether a transiting planet is orbiting pro or retrograde by watching how it distorts the star's light spectrum. The signal was unambiguous. The planet runs backwards. Here's the thing. The leading theory for retrograde orbits involves a third body, another planet, or a companion star, gravitationally kicking the planet into a tilted, eccentric orbit over time. There is a faint companion star in this system, an M-dwarf, detected about 1,600 astronomical units away. That's a long way. Long enough that its influence over millions of years is plausible, but it hasn't been confirmed as the culprit. Something flung this planet into its current path. The planet is now spending the next billion years slowly spiraling inward through tidal forces, its orbit gradually circularizing, until it becomes a hot Jupiter, hugging its star in a tight, close loop. We are watching a transformation in progress. And somewhere in that system, the suspect that kicked it into this trajectory may still be lurking, undetected, just waiting for us to look in the right direction. Number 3, the impossible planet. Here is a fundamental constraint of planetary science, stated as simply as possible. When a star forms, the gas and dust left over around it, the protoplanetary disk, has a fixed amount of material. The more massive the star, the more material in the disk. The less massive the star, the less. Small, cool red dwarf stars have thin, mass-poor disks, which means the planets that can form around them are small, rocky, modest. That is what the math says. That is what the models produce. And for decades, that is what we found. Then, November 2023 happened. A team at Penn State, using a custom-built spectrograph called the Habitable Zone Planet Finder, mounted on the Hobby-Eberly telescope, announced the discovery of LHS 3154b. The star it orbits, LHS 3154, has 11% the mass of our Sun. It is one of the coldest, dimmest, lowest mass stars we know of, 100 times less luminous than the Sun. The planet is 13.2 times the mass of Earth, Neptune scale, and it orbits that tiny star every 3.7 days. Lead researcher Suvrith Mahadevan put it as plainly as science writing ever gets. The planet-forming disk around the low-mass star LHS 3154 is not expected to have enough solid mass to make this planet. But it's out there, so now we need to re-examine our understanding of how planets and stars form. The disk that surrounded this star when it formed, running the models forward from what we know about stars this size, should have had roughly 1/10 the solid material needed to build a planet this massive. The planet would have needed 10 times the available supply. And somehow, it exists anyway. That should have been a once-in-a-career discovery. A landmark paper. A single, extraordinary exception that astronomers would spend years trying to explain. Then, June 2025 happened. A different team at University College London, the University of Warwick, the University of Birmingham, and several other institutions published a paper in Nature Astronomy about a planet called TOI 6894b. It orbits a red dwarf with 20% the mass of the Sun. Slightly bigger star than LHS 3154. Still tiny. Still far below what formation models consider viable for giant planet formation. The planet has roughly 50% of Saturn's mass and a radius slightly larger than Saturn's. It orbits its star every 3 days, and when it passes in front of that star, it blocks 17% of the star's light. 17%. Most planetary transits dim their star by less than 1%. The reason TOI 6894b blocks so much is that the star is only about 2.5 times wider than the planet. The star is only 2.5 times wider than the planet it somehow produced. Edward Bryant at UCL, who screened over 91,000 red dwarf stars in test data to find this system, said, "We did not expect planets like TOI 6894b to be able to form around stars this low mass." Neither discovery has a satisfactory formation explanation. Both lead teams, independently across different institutions, in different years, published papers essentially concluding the same thing. Our models are incomplete, and these planets should not exist by the rules we thought we understood. Two separate research groups, two separate systems, two planets that each, on their own, would have been landmark exceptions, and the universe produced both of them. The uncomfortable question, the one that nobody has answered yet, is whether these are rare exceptions at all. The most common stars in the Milky Way are small red dwarfs. We've barely surveyed them. If a small percentage of them host giant planets that our models say are impossible, there could be more of these impossible worlds than we've imagined. Hiding around the most common stars in the galaxy, in plain defiance of everything we thought we understood about where planets come from. Number 2. The lava world that builds its own sky. 41 light-years away, orbiting a binary star system in the constellation Cancer, there is a planet that should be a dead rock. The math is unambiguous about this. 55 Cancri E is a super-Earth, about twice Earth's size, nearly 9 times its mass, and it orbits its star every 17.5 hours. That orbital distance works out to roughly 2.25 million kilometers from its star. Mercury, for scale, orbits at about 58 million kilometers. 55 Cancri E is orbiting about 25 times closer than Mercury orbits the Sun. At that distance, the dayside temperature exceeds 3,000 Kelvin, 5,000 degrees Fahrenheit. The surface is not solid rock. It's a global magma ocean. The planet is, by any conventional definition, a lava world, and it has an atmosphere, not a trace. Not a wisp. A substantial, detectable, confirmed atmosphere, observed by the James Webb Space Telescope in observations from November 2022 and March 2023, with results published in Nature in May 2024. Lead author Renyu Hu at JPL described it as a volatile-rich atmosphere, likely rich in carbon monoxide or carbon dioxide. This is genuinely extraordinary. Ultra-short period rocky planets, the ones closest to their stars, receiving the most radiation, are not supposed to have atmospheres. Stellar radiation strips them, especially at these temperatures, especially at this orbital distance. The rule is fairly simple. The hotter and closer you are, the faster your atmosphere gets blasted away. 55 Cancri E should have lost any atmosphere it ever had billions of years ago. There shouldn't be anything left to detect. And yet, Hugh's team's explanation is that the atmosphere isn't a leftover. It's not a remnant of some primordial envelope. The planet is continuously building a new one, from the bottom up. The magma ocean below is outgassing, releasing volatiles trapped in the molten rock, pumping carbon compounds up into the atmosphere to replace what's being lost. It's a feedback loop in the other direction from the disintegrating planet we discussed earlier. Instead of losing material and accelerating its own death, this planet is losing atmosphere and replenishing it in a constant geological churn. Hu put it simply, we envision that the atmosphere is supported by the magma ocean down below. But here's the thing. The planet's infrared brightness, the amount of heat it radiates, fluctuates by a factor of 6 on timescales of days. Not years. Days. For comparison, Earth's thermal output is extraordinarily stable over human timescales. The only proposed mechanism that could cause a planet's infrared brightness to vary that dramatically, that quickly, is volcanic activity. Eruptions massive enough to temporarily blanket the entire planet in ash clouds, altering how much heat it radiates. Globally, then clearing, then recurring. No other exoplanet behaves like this. There's a planet 41 light years away that is perpetually on fire, perpetually losing its sky, and perpetually rebuilding it from its own molten surface. It's been doing this for billions of years. Every few days, something shifts, something erupts, the sky changes, then the cycle starts again. We are not looking at a dead world. We are looking at a world in continuous, violent conversation with itself. Number 1. The planet that shouldn't be anywhere. Start with the star, because the star is important. A millisecond pulsar is what remains when a massive star, much larger than our sun, reaches the end of its life, collapses in a supernova, and leaves behind a neutron star that spins hundreds of times per second. The one we're talking about, designated PSRJ 2322-2650, completes roughly 300 rotations per second. It has approximately the mass of the Sun. It is approximately the size of a city. It is an object of almost incomprehensible density, radiating gamma rays and high-energy particles, spinning so fast that if you put a clock on its surface, relativistic effects would make it tick measurably differently than a clock anywhere else. It is a dead star, a remnant, a cinder that refuses to stop moving, and somehow it has a planet. The planet, PSRJ 232-2-2650b, was first detected in a radio survey in 2017. Jupiter mass object, confirmed companion, unusual. Pulsars occasionally have planets. The very first exoplanet ever discovered, in 1992, orbited a pulsar. But a gas giant scale planet around a millisecond pulsar is exceptionally rare. Strange enough already. Then, in November of 2024, the James Webb Space Telescope observed it. The results were published on December 16, 2025, and the team's initial reaction, captured for the record by Peter Gao of Carnegie Science, was, quote, "What the heck is this? The atmosphere of this planet is dominated by helium and molecular carbon. Not water vapor, not methane, not carbon dioxide. The things you'd expect. Not even hydrogen in its usual form. helium and molecular carbon. Diatomic and tricarbon compounds, present in a detectable atmosphere at temperatures ranging from 1200 degrees Fahrenheit on the night side to 3700 degrees Fahrenheit on the day side. Those temperatures should destroy molecular carbon. At that heat, carbon bonds to other elements, oxygen, nitrogen, hydrogen. It doesn't remain as pure molecular carbon. And yet, Roger Romani of Stanford, one of the world's leading experts on these kinds of pulsar systems, proposed a possible explanation involving the crystallization of carbon-oxygen mixtures deep within the planet's interior. A process where pure carbon crystals float to the top and get mixed into the helium atmosphere. It's plausible. It's not proven. And even he acknowledged that the complete absence of nitrogen and oxygen in the atmosphere has no clean explanation. Quote, "Something has to happen to keep the oxygen and nitrogen away. Now, add the shape. The planet orbits just 1 million miles from its pulsar. Our moon is 239,000 miles from Earth. This planet is roughly 4 moon distances from a dead star that has the mass of the sun. The tidal forces at that distance are enormous. The gravity pulling on the near side of the planet is significantly stronger than the gravity pulling on the far side, and that differential is physically stretching the planet. It's not a sphere, it's a lemon. Elongated along the tidal axis, flattened at the poles, by roughly 38% more diameter along the equatorial stretch than the polar one. A lemon-shaped planet raining diamonds. It completes one full orbit every 7.8 hours. A year for this planet is shorter than a workday. Now here's the observation geometry. The James Webb Space Telescope cannot see the pulsar at all. JWST is an infrared telescope. The pulsar emits gamma rays. Gamma rays are invisible to JWST's instruments. There is literally nothing there from JWST's perspective, a blank in the sky where the host star should be. What JWST can see is the planet, lit by radiation it can't directly observe, radiating heat from a source that is invisible to it. Michael Zhang at the University of Chicago, the principal investigator on the study, described it. The planet orbits a star that's completely bizarre. The mass of the sun, but the size of a city. This is a new type of planet atmosphere that nobody has ever seen before. He also noted in the understated language that scientists use when they genuinely don't know what they're looking at. How the planet came to be is a mystery. There is no existing formation theory that cleanly accounts for a gas giant orbiting a millisecond pulsar with this atmospheric composition. Pulsars are the remnants of supernovas. The supernova that created this one would have released enormous amounts of energy. It should have destroyed anything orbiting nearby. Either the planet formed before the supernova and somehow survived it, which would require its orbit to be essentially untouched by a stellar explosion, or it formed after, from the material ejected by the explosion itself, which would require gas giants to form through mechanisms we've never observed. Or it was captured from somewhere else entirely, which introduces its own gravitational difficulties. None of these are comfortable. None of them have been confirmed. And so we are left with a lemon-shaped, diamond-raining, helium and carbon-enveloped, gamma-ray-heated world, completing a full year every 7.8 hours, around a dead star, spinning 300 times per second, that we cannot even directly observe. Studied by a telescope that sees everything around it clearly and is completely blind to the thing at the center. This is where the list ends. But the thought doesn't. We built our understanding of planets by looking at 8 of them. 8 data points in one system around one star. From that, we drew rules. And for a while, those rules worked. They worked well enough that we felt confident applying them to the rest of the universe. PSRJ 2322-2650b is not a glitch. It's not a measurement error. It's a confirmed object, peer-reviewed, published, observed by the most powerful space telescope ever built. And it doesn't fit. Not at the edges. Not slightly. It doesn't fit anywhere in the framework we constructed. Neither do the others. Each of them bends or breaks a different rule. The rule about what density planets can have. The rule about where giants can form. The rule about what direction orbits run. The rule about what stars can host planets. The rule about whether rocky worlds can hold atmospheres. The rule about what materials an atmosphere can contain. We have 5,800 confirmed exoplanets now. We've surveyed a fraction of 1% of the stars in our galaxy. The rules we wrote were always provisional, always built on a sample size too small to be confident in. Every one of these planets is the universe sending back a correction, not to discourage us, but to remind us that description is not explanation, that naming a thing is not the same as understanding it, and that the rulebook we've been carrying was always a rough draft. We've got 5,800 planets, and we don't understand